Hello and welcome to Science with Mrs. Blackburn. Today we are going to be talking about the solar system. And this is a topic that has a lot of misconceptions that go along with it. But today we are going to knock out those misconceptions and we are going to talk about the actual structure of our solar system and how it formed. So our goals for today, for this video, are being able to describe the structure of the solar system and then discuss how gravity works. We're also going to explain a little bit how our solar system formed. We're not going to go really deep into that one today, but we will probably do a second part to this video to tackle that second learning target a little bit more. So let's go ahead and get started. When you think of the solar system, you probably think of something like what you see here on the screen. Maybe you had done a model at some point when you were little about the solar system and you had the little foam spheres with little toothpicks on them and you labeled all the different planets. Or maybe you're even thinking of something like one of these diagrams, a poster of some sort that you might have seen in a science classroom before. Well, these two models are good models of the solar system because they let us know which planets are in our solar system. They also model how the planets revolve around our sun, but these models do have some limitations to them. So today we really want to talk about the actual structure of our solar system. But before we do that, let's talk a little bit about gravity because we have to understand the force of gravity in order to understand how our solar system works. So gravity is just a force. A force is a push or a pull, but gravity is a natural force that every object exerts on all other objects. Now, I said that correct. Every object exerts gravity on all other objects. Sometimes we think of gravity as being something that the Earth exerts on us, but we also exert gravitational forces around us. Hey, even atoms, tiny little things, exert gravitational forces on each other. The thing about it is to us, gravity is the down pulling force that's pulling us toward Earth. And the reason why is because the Earth is so big. More on that later. So the force of gravity between two objects depends on two things. So forces have different strengths. We can have really strong forces and very weak forces. And the strength of gravitational forces depend on the masses of the objects and the distance between them. The masses of the objects and the distance between them. So here's a little diagram that just kind of shows that. Of course, the force of gravity acts between all objects. If mass increases, the force of gravity also increases. So bigger things will exert greater gravitational forces. That's why we can only feel the gravitational force of our Earth on us, because the biggest thing around us, the biggest thing that we're in contact with is the Earth. So of course that force is going to feel very strong to us. Smaller things exert less gravitational force. So even though you actually exert a gravitational force, when people walk around you, they're not going to be like attracted to you because it's such a weak gravitational force. Now, the other part of this is if distance increases, the force of gravity decreases. So that we would call that an inverse relationship. If distance increases, force of gravity decreases. The farther away something is, the less we feel its gravitational pull. We've talked in class about how there are stars that are way, way bigger than our sun, which is a star. And although those stars are really, really big and they would have a massive gravitational pull, we are not affected by that gravitational pull of those giant stars because we are so far away from them. The distance is so great that the gravity is very small in that case. So let's talk about the sun for a few minutes. So the sun is the largest object in our solar system, a diameter of 14 million kilometers. Now, a way to think about that, when we think about kilometers, because again, in science, we use the metric system. Imagine one of the meter sticks we have in our classroom. Imagine 1,000 of those. 1,000 of those is just 1 kilometer. So we're talking about something very huge. Now, in miles, that would be 8,699,196 miles. That is giant. Now, it is a star. The sun is a star. It's not a planet, not a moon. It's a star. And it's made mostly of hydrogen gas. It is a giant flaming ball of gas up in the sky. And it is so large that it makes up about 99% of our solar system's mass. So think of all the other planets, all the other debris and dust and meteors and asteroid belts and everything that we're going to talk about in that solar system. Our sun makes up 99% of the mass of our solar system. It's that much larger than everything else. Now let's talk about this process. Now, what makes the sun so bright and so hot is a process called nuclear fusion. And this is a process that's going to release so much energy. That's where we're getting all that light and heat energy that's actually powering our Earth. Nuclear fusion is a process where hydrogen atoms will basically run into each other at super duper fast speeds, and they will fuse into an atom called helium. Okay. And so when this process occurs, there's a great energy release in the form of heat and light. So we can thank the process of nuclear fusion for all the energy we have on Earth and the life on Earth. Now, the sun exerts gravitational forces on all the objects in our solar system, and that causes all the objects to orbit it. That's why we call it a solar system, because the sun really is at the center of our solar system. It's right there in the middle. And because it's so big, again, we talked about before, the bigger things are, the larger the gravitational forces. Because the sun's the biggest thing in our solar system, everything else is going to orbit the sun. So let's talk about planets now. A planet is any object that's going to orbit the sun and has a nearly spherical shape. A sphere is a ball. The mass of a planet has to be much larger than the total masses of objects whose orbits are nearby. I want you to keep that in your back pocket because this is going to come up when we talk about Pluto. So our solar system has 8 objects that basically fit these criteria. And again, orbit the sun, spherical shape, has a mass larger than the total masses of nearby objects. We have 8 of those. All right. So the 8 planets that we have are going to be Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Okay, those are our 8 planets. You need to know those: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Now, let's talk about where these are, because we actually categorize them. If you notice in this diagram, you might see that some of them are categorized as inner planets and some of them are categorized as outer planets. So let's see what that would look like. Now, this model, we're getting closer to a more accurate model of our solar system. So our solar system is organized into 2 main sections. First of all, if you look right here in the middle, remember we said that every planet is going to orbit the sun, okay? Every planet's going to orbit the sun. The sun is in the center of our solar system. Now, the first 4 planets that orbit the sun are going to be Mercury, Venus, Earth, and Mars. Those are called the inner planets. Now, the next 4, Jupiter, Saturn, Uranus, and Neptune, those are called the outer planets. Now, I want you to notice a few things about this diagram. It shows all 8 planets together. First of all, look at how far apart all these planets would have to be. They even had to kind of do a little magnifying of the inner planets just so we could see the outer planets, okay? The inner planets are way closer together, okay? There's the sun right there in the center, and the outer planets are way farther apart. Now, this diagram is still not to scale because notice how small the sun appears in this. Again, the sun is making up 99% of the mass of our solar system. So here we can see that this is obviously not a scale diagram. That is one of the limitations of this model in this particular picture. So let's talk more about these inner planets, Mercury, Venus, Earth, Mars. They're the closest to the sun. They are made mostly of rocky materials. Obviously, the Earth, we've talked about the structure of the Earth. We have our crust, our mantle, outer core, and inner core. We're made of rocky materials, and inside of us is, inside of our Earth, is molten rock in the form of the mantle and the outer and inner core. So Mercury, Venus, and Mars are similar to Earth, as in they're made of rocky materials. The outer planets, these are the 4 planets farthest from the sun: Jupiter, Saturn, Uranus, and Neptune. Now, these are different. They're going to be made mostly of ice and gases such as hydrogen and helium. Now, again, the sun is made of hydrogen and helium as well, but these planets are not doing nuclear fusion like the sun. They are not stars. They are planets, okay? The hydrogen and helium are just kind of hanging out there. Those things are not doing nuclear fusion. We call the outer planets the gas giants. They are not very dense. They are huge, but because they're made of gas, all the particles of gas are kind of farther apart. And so they're not very dense, but they are really, really, really big. So we also have so actually, let's look at one more diagram, okay? So here is, we're getting closer and closer to a more accurate diagram. So we started with, just so to go back, we started with that in our mind, okay? We learned a little bit more about how all this works, and then we made it to this. This is a little bit more accurate. Let me show you another one. We got some other stuff in the solar system that is in addition to the planets. There's more than just planets in our solar system, okay? So, of course, we have those inner planets here on the left. Then we have our outer planets. But if you notice, between the inner and outer planets, we have something called an asteroid belt, okay? Asteroids are basically rocks that are floating around in our solar system. They are kind of like debris, okay? And so we have an asteroid belt between Mars and Jupiter. Now, if you notice here, we've got some other stuff in there. You see a little thing called Ceres. Look how tiny it is compared to Mars. And again, this isn't totally to scale, but it gives you an idea. And then if you look over here on this more comprehensive diagram to the right, now again, this right here is a magnification of what we see in the middle. Now, if we zoom out here, you're going to notice, look at this. We have another asteroid belt, okay? This one's called the Kuiper belt, okay? And so we have 2 asteroid belts in our solar system. Now, along that outer asteroid belt, you're going to see some more objects. We have Pluto. We're going to talk about Pluto here in a second. We also have their Ceres again in that inner asteroid belt. We have Mackay is how you pronounce that. It looks like make, but it's Mackay. And then we have Ceres, we have Mackay, we've got Pluto. And then over here, all the way out here, we have something called Eris, okay? Right outside of all these outer planets, okay? So we've added some other little planets, and we've added 2 asteroid belts to our structure of the solar system. Again, the point of this is we want to be able to describe the structure of our own solar system. And now we know that if we're going to do that successfully, we're going to have to be talking about asteroid belts and some of these other little planets. So what are those little planets? We call those dwarf planets. Dwarf planets are similar to regular planets, as in they're spherical, okay? But they have some differences, okay? First of all, they're not a moon of any planet. Now, a moon is going to be an object that will actually orbit a planet. A moon will orbit a planet as it orbits the sun. Now, we've already talked about how we have our moon that is going to orbit the Earth as we orbit the sun, right? Okay? Now, a dwarf planet is not a moon. It's not orbiting another planet. It's actually orbiting the sun just like the other planets. But here's the thing, it does not have more mass than nearby orbiting objects. If you notice, all of our dwarf planets in that diagram, they're going to be found within those asteroid belts. What that means is that their mass was not big enough to exert a large enough gravitational force to pull all of these rocks, all of these materials in the asteroid belt into that planetary body. Okay, so its gravitational force is not big enough. Remember, gravity depends on mass and distance. It's close to all these asteroids, but it's not big enough to pull them in to itself. Okay, now back to this slide again. We've got Ceres, Eris, Pluto, and Mackay are our dwarf planets in our solar system right now. Ceres, Eris, Pluto, and Mackay. Okay, now if you notice this, they are pretty small. This is Mercury, our smallest planet for comparison. All of these are way smaller. Now look, Haumea is another one that's an asteroid actually. Haumea is an asteroid. That's why it's that egg shape. It's not a spherical shape. So that is just for comparison. We even have an asteroid that is bigger than some of our dwarf planets. Okay. And so that's what makes Pluto a dwarf planet. A lot of people want to argue the whole Pluto thing, but it's not really an argument. It's just as far as classification. Pluto is still there, but Pluto is not considered a planet because look where Pluto is on this slide. Look where he is. He's right in the middle of this Kuiper belt, and he's got all these asteroids around him, all this rock and all this debris that he just was not large enough to generate a big enough gravitational pull to pull all those back in there. So that's why Pluto is not considered a planet, okay? Now let's go to this slide right here, asteroid versus comet. An asteroid is going to be more of a rocky material, okay? Comets are more like ice and gas, and comets are very, very fast. Now, an asteroid is going to go in an orbit around the sun, but an asteroid's orbit is going to be, a comet's orbit around the sun. It will also orbit around the sun, but it's going to orbit kind of at the edge of the solar system in a very, very elliptical orbit. Now, the planets do kind of have elliptical orbits at times, okay? However, a comet's orbit is going to be very super elliptical. That's why when we hear about things like Halley's Comet, it's only going to be visible from the Earth every, I think it's like 80 some years. I'd have to look that one up. But a comet is going to have the coma, which is the solid part. It's going to have a gas and dust tail, okay? A lot of people think when they see a shooting star, they're seeing a comet. It's not the same thing. Shooting stars are actually meteors, which are basically space rocks that are falling within our Earth's atmosphere and burning up on entry. All right, so now that we've talked about the structure of our solar system, let's talk about some history behind that, okay? Now we have some early models of the solar system. We did not always know that the solar system was structured as it is. We've talked about this in science class before. As we gain more knowledge and more technology, we're able to find out more things. So our body of evidence and knowledge changes as time goes on, which is good. So before the 1500s, it was just thought that the Earth was the center of the universe. That makes sense. We've talked about how the Earth spins on its axis. It rotates, which makes the sun and the stars and the planets appear to be moving across the sky. Well, that's called the geocentric model. It actually makes a whole lot of sense if the only thing you know is that I'm standing here on Earth. Those things look like they're moving. The Earth must be the center of all of this. So we don't want to, bash these early people for thinking this. It made good sense. However, in the early 1500s, a scientist named Nicholas Copernicus proposed that the Earth and other planets moved around the sun, being the heliocentric model. If you see the word HELIO, like a helium, the word helium is from the sun. Okay, that's helio, meaning sun, centric model. Okay, so geo means Earth, helio means sun. So Copernicus said, hey, I don't think it's the Earth that's the center of the solar system. I think that it is the sun. And so that's an important thing for us to know. So we also have some other scientists that aren't on this slide that I want to tell you about. We have Kepler, okay? And actually, I do have a slide for it. In the 1600s, a scientist named Johannes Kepler discovered that the planet's orbits were ellipses, not circles. Now, an ellipse is going to be kind of between a circle and a football shape, okay? And so an ellipse contains 2 points called foci, okay, which is the singular for the word focus. And they're going to be equal distance from the center of the ellipse and determine its shape. And so what he also discovered is that a planet's speed will increase the closer it is to the sun, okay? Like, for example, Mercury is going to move the fastest around the sun. First of all, it's going to have the shortest orbit because it's the closest, okay? Imagine that you're running around a track and you're closest to the center field. You're going to make it around that track faster than people in the outside lanes if you start at the same place. And so he discovered that a planet's speed increases the closer it is to the sun. This is also because that gravitational pull from the sun will be stronger for those inner planets because, again, gravity depends on mass, but also distance. The one that is not on the slide is in the mid 1700s, we had a scientist named Immanuel Kant, and he developed what we call the Nebular Hypothesis. And that helped explain the origin of our solar system. Where did our solar system come from? It looks like something happened to give us this pattern of these close rocky inner planets and these huge gaseous, far apart outer planets. And so Immanuel Kant developed this nebular hypothesis where he proposed that matter in the solar system began as a tiny particle of gas and dust, tiny particles of gas and dust called the solar nebula. And so he suggested that solar nebula started again. Gravity is going to be dependent on mass and distance. He thought that that solar nebula started collecting more and more mass, more and more matter, and eventually got larger over time. And so that will kind of have to be its own video because we need to talk about that later. Well, again, let's see if we changed our mind any. Our learning target was to be able to describe the structure of the solar system. We did talk a little bit about how our solar system formed with that nebular hypothesis, but also we learned a lot about how gravity works. And I hope that you went in this video from thinking about the solar system in these terms with those two models to more of this more accurate model here. So thank you for watching, and I will see you next time.